Hello. In this presentation, I will talk to you about our paper called Mining Minimal High Utility Item Sets. This paper is about data mining, about finding patterns in data, and in particular, we want to find some type of pattern called the high utility item set, the minimal high utility item set. So first, let me explain to you what is a high utility item set. The problem of high utility item set mining is defined as follows. The classic example is to use high utility item set mining to analyze the data from some customers who are shopping. For the input of this problem is a transaction database, as you can see on the table on the top left. Here we have a database with 5 transactions, T1 to T5, made by some customer which have went to the store and bought different products. So for example, if you look at the transaction 1, we have that the customer bought some item A, like apple, and we have some quantities like 1. So the customer bought 1 apple. With 5B, for example, 5 bread, 1 box of cereal, 3 units of D, 1 unit of E, and 5 units of F, for example. So in the transaction database, we have transactions, and we have the items, the products that some people have bought, with some quantities about how many units they have bought, like 5 apple and so on. And on the top right, we have also a unit profit table. That means if you sell, for example, 1 apple, how much profit do you earn, for example? So here, we know that the profit of item A is 5. That means if we sell 1 apple, it's $5 profit. B is $2, C $1, and so on. So having this data about what the people buy, for example, in a store, we need to set a parameter we call the minimum utility. That means, for example, the minimum amount of money. So you can think about utility as in terms of money. Okay. So the goal of high utility item set mining is to find the patterns that generate at least this minimum amount of money. And the minimum utility must be a positive number, of course. So in my example, if we set the minimum utility threshold to $33, we will find all the patterns that generate at least $33 in the database. So for example, if you look at the bottom here, there are only 4 patterns. This is the solution to the problem. So we know, for example, that BDE make more than $33. It makes $36 actually. BCD has a profit of $34 and so on. So in high utility item set mining, if we apply this to a transaction made by some customers, we can find all the sets of products purchased together that generate a high amount of money, for example. Okay, so maybe now you want to ask me, how do we calculate the utility? Because I give you like BDE $36, but I did not explain how to calculate. So I will explain this to you next. Okay. So how to calculate the utility? I will give you an example. If we look at the item set B, D, E, that means we buy the item B, D, E together. Some customer buy them together in a transaction. So if you look at the transaction database, we need to find all the transactions that contain B, D, and E together. So B, D, E together appear in transaction 1 and 2. I have highlighted these occurrences there. Okay. So how to calculate the utility of BDE? It is the amount of money in transaction 1 plus the amount of money of BDE in transaction 2. In transaction 1, we have 5 units of B, and they have a $2 of unit profit, so 5 multiplied by 2. Then for D, we have 3 units of D for $2 each, so plus 3 multiplied by 2. And then for E, we have 1 unit of E with a $3 unit profit, so plus 3 multiplied by 1. So this is the amount of money yield by BDE in transaction 1. So we do the same for transaction 2, and we know that the total amount of money in this database for BDE is $36. Now, I explained already what is the problem of high utility item set mining. We have database with information about the money, the utility, and we want to find all the sets of items purchased together that makes a lot of money or have a high utility. I want to say also that although in my example I use the profit as a measure and I talk about customer transaction, we can apply high utility minings to other domains. So the utility could also be, for example, the time spent on a web page, and A, B, C, D, E could be web page instead of products, for example. So this is quite a general problem, but the classical example that we use is about shopping, actually. So now I want to talk to you about the challenge of high utility mining. About why high utility mining is a difficult problem actually to solve. So one challenge is that the utility measure is not monotonic or anti-monotonic. So what that means, okay. So it means if you have an item set like BDE with a utility of $36, for example, if you look at the superset of BDE or the subsets of BDE, then these subsets or supersets can have a utility that is higher, greater, or smaller than BDE. Okay. So for example, here we have BDE, $36. If we look at the superset of BDE, like A, B, C, D, E, it has a smaller utility, $25 only. And the subset of BDE, like BD, can also have a smaller utility than BDE. So because of this, when we search for the patterns to find the solution to the problem, it is very difficult to reduce the search. So for example, if we know that BD is not high utility item set, still the superset of BD, like BDE, can still be a high utility item set. So because of this, it makes it difficult to search for the patterns and find only the high utility patterns, okay. So, the one problem about high utility item set mining, it is that high utility item set mining is very useful actually to find the sets of items, the item sets that make a lot of money. But one problem is that it can find a large amount of item sets. So, depending how we set the minimum utility threshold, we can find, for example, thousands or millions of item sets. So if we find so much patterns in our data item sets, then it becomes very difficult for the user to look at these patterns and learn something from them. There are just too many, okay. And some of these item sets that we can find are sometimes redundant. That means we find some patterns like AB, but another like ABC, and AB is contained in ABC, for example. So maybe we can say that why we have both AB and ABC, for example. Okay. So this is just some main idea. Okay. We find maybe too many patterns, and we want to find like a summary of this pattern instead, to make it easier for the user to understand the patterns. So our solution, one solution, not just our, but a solution in general, is to find some summary, some concise representation of high utility item set. So there have been a few previous work on this topic. In the other papers, some people have proposed to find the maximal high utility item set, for example. So that means some high utility item sets that are not included in another high utility item set. So we try to find the largest one, in other words, or the closed high utility item set. So that means the high utility item set that have no supersets appearing in exactly the same transaction. So, and also another paper, we defined the generator of high utility item set. And So these are basically different kinds of summary of the result that we can show to the user. So we show less pattern to the user, and we try to remove some redundancy. Okay, so although there have been several work about finding some concise representation of high utility item set, one problem is that often they will find many long item set. So for example, if we find the maximal high utility item set, we try to find the largest one, like A, B, C, D, E, F. So you can find the item set with 7 or 10 items, for example. So this actually, we think that it's not very good, because if you find a pattern like people buy apple, bread, rice, noodle, and many other things together, then it becomes difficult for the user to use these patterns. So for example, can we promote 4 or 5 or 6 or 7 products together in a retail store, for example, like apple, bread, noodle, rice, and so on? It would be very difficult actually. So in this paper, we make a new proposal. We try to find instead the minimal high utility item set. That means the smallest sets of items that yield a high profit. So contrarily to the maximal high utility item set, we try to find the smallest one that make a lot of money. Because if they are small, the item sets, maybe they are easier to promote together if we want to do some promotion to make more money, for example. So this problem of the minimal high utility item set has not been considered in the previous work. Okay, so what is a minimal high utility item set? The idea is very simple. It is a high utility item set that has no subset that is also a high utility item set. So for example, if you look at our example, we had 4 high utility item sets. Among them, the item set B, C, D, E is not a minimal high utility item set because it has some subsets that are high utility item sets. So for example, B, C, D, E is not minimal because B, D, E is also high utility item set. So we only keep the B, D, E, B, C, D, and B, C because those are minimal high utility item sets. So there are some interesting property about this new type of item set. One of the property is property 2. If an item set X is a minimal high utility item set, then all its subset and superset cannot be the minimum high utility item set. So if we find that AB is a minimal high utility item set, we don't need to look at all the supersets of AB, like ABC, ABD, and so on. So this is very useful to reduce the search space. Another property is property 1. If the minimal utility is lowered, the number of minimal high utility item set may increase, decrease, or stay the same. So this is very different from high utility item set mining. In traditional high utility item set mining, if we lower the threshold, we will always find more pattern, or at least the same amount. But here, if we lower the threshold, the minimum utility, we can find less pattern because the reason is that we keep only the minimal one, actually. Okay. So, and in the special case where the minimum utility is set to 0, the number of minimal high utility item set is equal to the number of items because they are the smallest item set, the minimal one in the database. Okay, so let me explain to you a little bit about how our algorithm called MinFHM works. Okay, so I will just give the main idea because actually there's a lot of details, but you can also look at the paper if you want to know more about this. And also, you can also look at the source code of MinFHM in the SPMF software if you want to know more about this algorithm. So it is an algorithm to find all the minimal high utility item sets. So if we give the database the threshold, the minimum utility, it will find exactly the solution to the problem. It is based on the FHM algorithm for high utility item set mining, which is one of the fastest algorithms for high utility item set mining. And how it works, it do a depth first search. So here on this picture here, you see the search space for all item set with the items A, B, C, D as example. So we can see this as a tree, the search space. Okay, we call this a set enumeration tree actually. So at the root of the tree, we have the empty set. Then we have the single item like A, B, C, D, and then A, B, A, C, A, D, A, B, C, A, B, D, A, C, D, and so on. Okay. So for a depth first search, that means we start from the root, then we go to AB, ABC, ABCD. Then we go up, we go to ABD, then we go up, we go to AC, ACD, go up, AD, then go up, and then explore D, and so on. Okay, so this is a depth first search. Okay, and then because there are so many possibilities, and we don't want to look at all of them, we will apply the pruning property 1 and 2 to reduce the search space. So for example, if we find that B is a minimal high utility item set, because of property 2, we don't need to look at BC, BD, and BCD. So we can reduce the search and still find the solution to our problem. Okay. So why it is important to reduce the search? It is because the search space is very large actually. So here in this example, we have only 4 items, A, B, C, D. But if you have, for example, 1,000 items, then the search space will contain about 2 to the power of 1,000 possible item set, okay, actually. So the search space can be very large. We don't want to look at all the possibilities. So we apply property 2 to reduce the search space. If an item set is minimal high utility item set, we don't need to look at the supersets. And also, because this algorithm is based on FHM, we also use an upper bound on the utility that can be used to reduce the search space. So here I will not talk into details about this because it was introduced in the FHM paper. It is not something new in this paper, but the idea is as follows. If you have an item set like B, we know that the utility is not monotonic. The utility of BC could be higher or smaller or equal to that of B. But we can calculate some upper bound that will tell us if all the extension of B, the subtree of B, can have a utility that is high or not. And then we can use this to reduce the search space. Okay. So again, here I will not explain the details about this, because it's not something new in this paper. It was in the FHM paper also and other paper before. So how it works? The main idea of the MinFHM algorithm, the first step is to scan the database to create a utility list structure for each item. So what is a utility list? It is kind of table. So for each item like A and D, we see here, we have a table. So if we look at the table of A, it has 3 columns, TID, utility, and remaining utility. The TID means the transaction where the item set A appear. So A appear in T1, T3, and T4 in our example. And in T1, A has utility of 5. In T3, A has utility of 5, and T4 it has utility of 10. And the column remaining utility gives beside A, after A in the transaction T1, for B, C, D, E, and F, there are $20 left. So this is the remaining utility. If we want to do extend A to do AB, AC, AD, in transaction 1, we only have $20 left that we could add to A to make a larger item set like AB, AC, ABC, and so on. So in T3 we have the remaining utility is 3, in T4 it is 12, and so on. And for item set D is similar. We know that D appear in T1, T2, T3, as utility of 6 in T1, 6 in T2, 2 in T3, and that in T1 the remaining utility, that means all items after D, like E, F, have a total utility of 3. In T2, the items after D, like E and F, have utility of 3, and in T3 there are no items after D, there's no E or F, and so on. So the first step, we create this table called utility list for each single item. Then, from this table, if we want to find the utility of A, we do the sum of the column called utility. So the sum here is $20, for example. And then for D, if we do the sum, we find that D has utility of $14. Now, if we want to calculate some upper bound to reduce the search space using the utility, so we can do like in the FHM paper. So we take the column utility, we do the sum of remaining utility, so $20 plus $35, and this gives you an upper bound. That means the upper bound here is $55. It means that any item set starting with A, like AB, AC, AD, ADF, cannot have utility more than $55. So this can be used to reduce the search space, for example. So if we say, for example, minimum utility is $60, we know that A and any extension of A cannot be the high utility item set. Now, after we created the table for the items like A and D, we can combine the table of A and D to get the table, the utility list of AD, for example. This is not a very complicated process. So actually we need to join the two tables. So you see A appear in T1, T3, T4, and D appear in T1, T2, T3. So we do the intersection of T1, T3, T4, and T1, T2, T3. So it will give you T1 and T3. For T1, we add 5 for item set A, and we add 6 for item set D. So 5 plus 6 equal 11. Then for T3 we add 5 and 2, so 5 plus 2 is 7. And for the remaining utility, we take the minimum of in T1 of 20 and 3, so the minimum is 3. And for T3, we take the minimum of 3 and 0, so the calculation is 0. So from this, we can find that the utility of AD is $18 by calculating the sum of the utility column in the table of AD. And also, we can calculate an upper bound for all the item set that start with AD, like ADE, ADF, and so on. So we find that all the supersets, not supersets, but the extension of AD cannot have more than $21 of profit or utility. Okay, so this is the basic idea of the algorithm. We do a depth first search, and then we create these kind of tables to calculate upper bounds on the utility that can help us to reduce the search space. And also we apply the property 2 that I presented before to also reduce the search space. So here I put the pseudocode of the algorithm, okay, but if you are interested about this, you should have a look at the paper, and also you can have a look at our SPMF software, which give you the source code in Java, and you can also run the algorithm from this software and try it by yourself with some data and so on, okay, if you are interested. Now we did some experiment to evaluate our new algorithm and new problem. So we use 4 databases used in the field of pattern mining. So 4 databases with different characteristics. Mushroom is a database about mushrooms. This database is not about shopping, but it is interesting because it is a dense database. So we want to try our algorithm on different kind of database, different characteristics. Concise is a database about clickstream on the website, the web page that people will click. Retail and Food Mart are 2 databases about shopping, actually. So Food Mart has the real utility values, and for the other database, we use some synthetic utility values as in previous work. Okay, so we did the different experiment, So what we did, we compared the MinFHM algorithm, our new algorithm, with FHM to find out the minimal high utility item set, CHUD to find the close high utility item set, and GHUI miner to mine the generator of high utility item set. And then we varied the minimum utility threshold and compared the execution time, the memory usage, and how many patterns we can find to see if we find the minimal high utility item set, can we find very small set of patterns that would be like a summary, for example. So first, let me show you some result in terms of execution time. If you look at the line with the square, it is FHM to find all the high utility item sets. So for example, on mushroom, we find that for some values, it takes about 100 seconds to find the high utility item set. While if we find the minimal high utility item set, it takes only 1 second. This is because of our new pruning property number 2, which is very powerful. When we find only minimal item set, we don't need to look at all the larger item set. So we can reduce the search space a lot. And if you look at the other lines with the triangle, this is the generator, and the circle, the close item set. The time, I mean, it is much faster actually if we use this. Okay. So overall, we find that MinFHM is up to about 800 times faster than the other algorithms. In terms of number of patterns, if we look at the line with X, we find that the number of minimal high utility item set can be up to 900,000 times smaller than the number of close high utility item set, minimal high utility item set. So that means we can eliminate a lot of patterns that are very large to find only the smallest one that make a lot of money, okay, or have a high utility. So this is all I wanted to present for today. I discussed a new task called the minimal high utility item set mining. I presented a new algorithm called the MinFHM algorithm for this problem. And we did some experiment to compare with other type of high utility item set like close or generators. And we find that our algorithm can be up to 800 times faster than these other set of high utility item set. And we can find a very, very compact set of patterns. Sometimes up to 900,000 times less pattern when we find the minimal high utility item set. So if you are interested about this, you can have a look at our SPMF data mining library. It offers a lot of implementation in Java of this kind of algorithm for high utility item set mining, and it also includes the MinFHM algorithm that I have presented here. So this is all for this presentation. Thank you for listening.